We'll start a new chapter today. It's just basically definitions and simple things. After the break, I'll make some reminders and we continue this discussion. So the chapter we're going to start is called the spectral. Well, it's about two concepts of eigenvalues and eigenvectors, or there's a general term which collects two of these in one single name. It's a term which I call spectral analysis. So I'm going to discuss matrices, and I'm going to discuss spectral analysis for matrices. However, given that what I mean is, however, this discussion can be transferred easily to linear maps, because now we know, I hope, that every linear map can be associated with a matrix. And then everything we say about matrices can be transferred to linear maps. Okay, so I'm going to discuss the spectral analysis for matrices, but it equally applies to linear map as long as you fix a matrix for that linear map. Something in this direction we've done, we did 2 days ago when we discussed with you nullities and ranks and null spaces and images of linear maps. Back then I said that nullity is one of these things, one of these invariant qualities of a linear map, which you define through a matrix associated with that linear map, but it's a thing which stays invariant. If you change the matrix but you keep the linear map, the quantity will not change. Spectral analysis is very similar in this regard. You define spectral properties of a linear map through a matrix of that linear map with respect to some basis, but many sides of the spectral analysis, they stay invariant. If you change the matrix but keep the linear map, the thing will stay the same. But let's just start with the simple basics. So from the matrix point of view, you start off with the square matrix, size n. That's how we normally define this set. F, as usual, it's either reals, complex, or rational numbers. The first concept you need to remember every time we are in the spectral analysis chapter, a number, normally we call it lambda, it's called eigenvalue of matrix A, if and only if you can find a vector in an tuple space, which on one hand is non-zero, and on the other hand, it works like this. Okay, that's a complete definition of the concept of eigenvalue. A number is called eigenvalue of a matrix if for that number you can find a vector, if you can, that's enough evidence, which meets these two requirements. It must be non-zero vector and it must be like this. And the first requirement is understandable, I hope, because if you just require this without insisting on non-zero vector, then you can always make this work with choosing a zero vector, right? If you choose a zero vector here and here, the identity will trivially be correct. On the other hand, if you have this extra, then this identity is quite non-trivial, and if you can make it work, then this lambda will be called eigenvalue. The vector itself, which makes it work, it's called eigenvector, or the full name will be eigenvector associated with the matrix A and eigenvalue lambda. So eigenvector doesn't exist by itself, it only exists in connection with some eigenvalue. Okay. This is one look at this at the idea of eigenvalue and eigenvector. A slightly modified look, slightly modified approach is here. Look at this. When you look at this identity, which is at the core of the idea of eigenvalue and eigenvector, you can transfer this identity slightly. You can say this one true if and only if this one is true. So you just move the things on the left-hand side. Then you just combine, because x present on both terms, you can just factor it out. Here's a factorization. In this place, I use, you see, identity matrix of appropriate size. That's what you're factoring out. And then what do we see? This is equivalent. We see that x is a vector which solves the homogeneous system like this, isn't it? And the vector itself is non-zero. we always know that zero vector always solves a homogeneous system, but this time we see, I mean, the lambda will be an eigenvalue when for this system with such a matrix, there is a non-trivial solution. So this non-zero vector x belongs to the null space of this matrix. So that's another slightly modified definition of the eigenvalue. It sounds like this. Alternative. A number, lambda, is called eigenvalue if and only if. A number lambda called is eigenvalue if and only if. If and only if E lambda, and E lambda is just a name, it's just abbreviation to this null space. If this E lambda is non-trivial, so if this subspace, if this null subspace is larger than the zero subspace. That is exactly here. If you have elements in that null space which are different from zero vector, this is the eigenvalue. So this definition, it avoids mentioning a particular vector. It just makes you test the size of this subspace. Sometimes this subspace, it's called the eigen subspace associated with the value lambda. I mean, if it is non-zero subspace, it's called eigen subspace of the value lambda. That's another term which I hope you'll remember. Okay. A few simple examples first, and then I'll show you a few simple examples actually. That's the simplest possible examples ever. If I take a matrix A like this, you see it's a diagonal matrix. All the non-zero elements are on the diagonal. I'd like to demonstrate these concepts on the example of this matrix. In this case, I just show you this. Look at this. If I make this testing, if I multiply my A matrix by E1 vector, E1 vector, if you remember, that's the standard basis vector in R2, two-dimensional space. It's a multiplication. So this is an E1 vector. This is A matrix. It's a very simple matrix multiplication, right? Isn't it? It's just the result will be this. That will be the result. If I alter this result slightly into this, I have exactly what is required, isn't it? Look at this. That's what's required for the number to be an eigenvalue. I need to present explicitly a non-zero vector, which works like that, and I have done so, isn't it? I presented a non-zero, E1 is a non-zero vector. You can't argue with this. I have presented this vector, which works exactly like this, you see? 1, 2. So this number, which appears here, A1, is the eigenvalue of my diagonal matrix A. I can make a similar presentation. So A1 is an eigenvalue, and the associated eigenvector is E1. This is another test. I can do a similar test with the second standard basis vector E2. Is a multiplication. It's another very simple case of matrix multiplication. The result is like so. And again, if I make a minor transformation of this result, if I use E2 again, if I use E2 again, this requirement of an eigenvalue becomes apparent, left-hand side, right-hand side. So I made an explicit presentation of a non-zero vector, E2, which works like this. And hence, I have full right to call this second number, A2, another eigenvalue of my matrix A. And the associated eigenvector is E2. A1 is another eigenvector, and E2 is the associated eigenvector. It's a very simple example, but it's one of the key examples in the whole spectral analysis theory. Even though it is this simple, one day you will learn that the whole idea of the spectral analysis is to make every matrix diagonal, and that's at the core of it. So if I use my third term, eigen subspace, I can say E1 vector is an element or is a member of eigen subspace associated with A1. You see, A1 is subindex, little e2 is the element of the eigen subspace associated with the value A2. Okay. In fact, this diagonal example I just showed you, it is two-dimensional. I intentionally chose it to be two-dimensional to make the presentation shorter, but if you think about that, there's nothing specific about this dimension 2. You can extend these ideas to any dimensions. You can take a matrix, you can take a diagonal matrix of any size, not specifically size 2. The whole thing will stay identical to this. So what I'm saying is this: if I introduce this notation, I don't know if you saw this notation before, but it is often convenient when you present or when you write a diagonal matrix, rather because it takes a lot of space when you write a square like this. So there is a shorter way to write a diagonal matrix like this. People write diagonal matrix and they just list diagonal entries, assuming that the rest of the entries are 0. So if you compare these two ways of writing diagonal matrix, this is a lot shorter. You can't deny that. But effectively, these are the same things. That's why I'm asking you, that's why I'm telling you. If you didn't see this before, this way of writing diagonal matrix, that's a good time for you to learn this way of writing and use it in the future. Right, so now if I use this notation of diagonal matrices to make my presentation a bit shorter, what I claim is these things which I've done for two-dimensional matrix, they will work equally well for if I take, sorry, that's what I say here by analogy. If I take a matrix, which is a diagonal matrix of size n, see? If I take a diagonal matrix of size n, and I hope now you know what this writing means, it means a matrix with all 0 entries except the diagonal entries, where the entries are A1, A2, and all the way until AN. So by analogy, if I take this n-dimensional diagonal matrix, I claim, by the same analogy as in here, I claim that if I start testing my matrix with the standard basis vectors, and you see again, all of the identities of this type, I just write them in one line using the J subindex here. If I test all of these EJ vectors with my matrix A, they all will work like that. And that will be the evidence that this number, the Jth diagonal entry in my matrix, is in fact eigenvalue, and the associated eigenvector is Ej. This is true for every j from 1 up to n. This is a pure analogy to this two-dimensional presentation. So in terms of the spectral structure, in terms of the eigenvectors and eigenvalues, diagonal matrices are the simplest there are. In your practice, in your study of spectral analysis in this course, you will need to find eigenvalues and eigenvectors for the matrices which are more complex, so not diagonal ones, and that's basically will be our first main objective, how to identify eigenvalues and how to find associated eigenvectors for the matrices which are different from diagonals, because diagonals, that's it, we've done it in full generality. All of the eigenvalues, all of the eigenvectors are here right in front of you. So I'll show you one example where the matrix is not diagonal, and then we will start developing like a more general approach to this. It's still on this slide, example 2. Any questions, by the way? Okay, so example 2 is this matrix. As a numerical example, 3 times 3 matrix. is the entries. What I'd like to do is actually, I'd like to test. There are some questions in the yellow book where the question is relatively simple because it just gives you the matrix. It gives you a candidate for an eigenvector, like in here. It's a candidate, and the question just goes to ask, verify or check, is it true or not, that the vector, that the supplied vector is in fact eigenvector, and find the associated eigenvalue. In that setting, the question is, it's a pure computation thing because all you need to do, you need to test something like this. And you got everything in your hands to do that because you know A, you know X. So you need to plug everything into this relation and see if it works. If you can guess a number, which make it work. And it's only one number to guess. Normally, when it's only one number to guess, it's very easy to guess. So here we go. I'll do the same. I'll do this check. So I'm plugging I start off with the left-hand side. I use my A, I use my X on the left-hand side. In fact, yes, I have the whole computation here on the slide in very expanded form. This is the first entry. I mean, if you use A here and X here, this is the first entry, dot product of this row and this column. This is the second entry, dot product of this row and this column again, and the last entry like so. All in all, if you do these computations, the result will be like this. 5 first component, 25 second component, and here I insist it will be 125. And then the last observation is whether this result of left-hand side computation whether you can make this result look like this with some choice of lambda. In this case, of course, the guessing of this lambda becomes easy, just 5. And that's the end of it. So the question was whether this vector is an eigenvector of this matrix. The answer is yes, because it makes such an identity correct. And the guessing for this lambda is 5. So the associated eigenvalue is 5 right from here. Right from here. Any questions? Well, these are the examples on the easier side of the spectral analysis. I mean, on the less computational side of spectral analysis. Diagonal matrices. Nothing can be easier than this. Basically, the entries on a diagonal, they are eigenvalues, and that's the end of story. This second example is just when you provided a vector to test, it's also easy. You just test the identity like this, which is at the core of the definition of the eigenvalue, and that's it. Now, I'd like to look into like a more advanced examples where you actually need to, when you don't have so much information given to you, like a vector to test, where you need to start off from the blank matrix and figure out eigenvalues and eigenvectors. For that, we need a little bit of preparation, and that's what we're going to do. Unless you have any questions in relation to this. All right. So at the core of the fully fledged search for eigenvalues and eigenvectors, the idea of characteristic polynomial. By now, probably you know that many things in mathematics is called characteristic polynomial. Like if you did your differential equations in calculus part, and there was, linear differential equations in the calculus part, and there was a characteristic polynomial there, which helped you to do that. There will be a characteristic polynomial here, which will help you to find eigenvalues and eigenvectors, even though right now you may think that they're just a coincidence. We use the same name for the characteristic polynomial in that case. There was, by the way, another time when we use the term characteristic polynomial, it is when we discuss with you dynamic systems, discrete and continuous time dynamic system. This was another instance where I used the term characteristic polynomial. these three instances where the term characteristic polynomial is used, you met in this topic, then the fact that we use the same term, it's not coincidental. With some effort, you can bridge all of these terms to the same idea, even though it's a difficult effort. But maybe some of you, I mean, at some time you will see this connection. Right now, you can think of it as a coincidental, of course. So there will be a third occasion where we're going to be use some polynomials, the one which we're going to call characteristic polynomial once again, and that will be the one which will help me to do eigenvalues and eigenvectors, and let's just look into that. So the whole idea of characteristic polynomial comes like this. So let me just start off again with the matrix. Square matrix of size n. A number is called eigenvalue, and this x will be associated eigenvector when the definition we just saw it, when the vector is non-zero and the vector is an element of eigen subspace, right? E lambda is the eigen subspace. The null space of A take lambda identity. It's a setting. This is a setting of my discussion from slide before. Square matrix, A number and a vector, and the connection between these two is here. Vector is non-zero and is an element of this subspace. In the subspace, that's the connection of the subspace to this number. Now we need to develop some test which will help us to identify these numbers. And that's how the test is normally developed. Look at this. We look at this fact, and that's something I have told you already. So the claim that this x comes from the subspace E lambda, given that E lambda is a null space of my matrix, of matrix A take lambda identity, this claim is equivalent to saying that x is a solution to this system of linear equation. I told this already in my slide before. I'm telling this again once over. It means that this system has a non-trivial solution. That's spelled out here. System of linear equations, homogeneous system of linear equations, has a non-zero solution. When this happens, we can say a lot about systems when this happens, because we've been studying such systems you've been studying such systems for quite some time. First semester you spent a lot of time on that. Up until now, we saw quite a few systems like this. What we can say about this is this. We can say that if I take this matrix to the row echelon form, symbolically, the result, what's going to happen with the result? What would be the what will be signifying this idea that the system has a non-trivial solution? That claim will be signifying that this row echelon form has a non-leading column, has some non-leading column, at least one non-leading column. That's one test we know from the past, which is equivalent to a system having a non-zero solution. Another test we know from the past. So this is equivalent to that test. Another test we know from the past is that rather than testing row echelon form, we can also test determinant. It's another very careful test, very sharp test, which delivers you whether this system has a unique solution or multiple solutions. Zero determinant, that is exactly the case of multiple, aka non-zero solutions. These two, you have to think of them you have to keep this in mind. Both of them, they are closely connected with many analysis many analysis you do when you search for eigenvalues or eigenvectors. But for now, we're going to look at the second one, because that's a good test, isn't it? I mean, look what we just discovered. If this number works like this, then this number must be something which works like this, and that's a completely numerical test. I mean, there's no any vectors here, there's no any vector spaces or null spaces in this test. This is just some number on the left-hand side, or in fact, you can think of it as a function, isn't it? You change your lambda a little bit, the determinant will be a different number, so it's a function of lambda, a numerical function of lambda, and it looks like those lambdas which you call eigenvalues will be solutions to this equation. This is a characteristic polynomial and characteristic equation I was talking about. the nature of determinant actually tells you that this function is nothing else but a polynomial, and hence I can tell you this theorem, which says lambda is the eigenvalue of a matrix when, or if and only if, this lambda is a solution to this equation. If you give a name to the left-hand side of that equation, it's a quite conventional name. The yellow book is very, I mean, it uses this notation quite often, and it reflects the dependence on the matrix of this left-hand side. This PA, it's a map which takes numbers into numbers, even though probably here I'm a little bit, yeah, numbers into numbers. That's right, actually, this is good. You can think of this PA, actually, this PA will be a polynomial. It's a symbol for polynomials of degree n. And that is something which is called characteristic polynomial of matrix A. That is something which is called characteristic polynomial of matrix A. So normally, I mean, like in your examples, in the examples in the yellow book, when the example goes to ask you to find eigenvalues, that will be the first method of finding those eigenvalues. You will need to compute this characteristic polynomial, this PA, through this formula, and then the next step will be finding roots of that polynomial, because this result tells you the roots of that polynomial are eigenvalues of your matrix. Even without actually finding the roots, we can say a little bit now about the eigenvalues. For instance, we can say that eigenvalues will always be complex numbers. Fundamental theorem of algebra, in fact, the one we discussed with you a while ago, tells us that there will be exactly n eigenvalues, right? Because every polynomial of degree n has exactly n solutions. Some of them may have some multiplicities, but we will have n complex numbers as solutions. We will have n eigenvalues. In fact, this multiplicity thing, which appears in polynomials, we transfer this idea into eigenvalues universe, and when you end up with the eigenvalue, which is a solution to your characteristic polynomial, and it is a solution of some multiplicity, we will say that the eigenvalue will have the algebraic multiplicity of this particular value. So I'll show you this a bit later. That's the term which we just borrow from our knowledge of complex polynomials. And in the realm of spectral analysis, we just add this prefix, algebraic multiplicity. The reason we add this prefix because there will be, in the realm of spectral analysis, there will be also geometric multiplicity, which is a bit harder thing, but we'll come to this. Example. Again, I'll start off with a simple example. I'd like to reconfirm first our diagonal example. Look at this. Here's my diagonal matrix. Let's just see what happens if I do this analysis on a diagonal matrix. You may think it's a bit redundant, because for the diagonals we discovered everything we could possibly discover in terms of eigenvalues and eigenvectors, but it just reconfirms everything through this new method, through characteristic polynomials. So look at this. If I build this matrix, A take lambda identity, this time it will be identity of size 2, is a matrix. It's still diagonal. Determinant of such matrix, here it is. So for the diagonal matrix, in fact, characteristic polynomial comes out already factorized. So in your search for the roots of this polynomial, you don't have to do anything because it's already factorized into linear factors. And here you go, you see so if you just ask the question when this polynomial is 0, you end up with two solutions, as those solutions we discovered sort of like by guessing before. Now we just discover the same eigenvalues already through robust mechanism. The mechanism which we call the characteristic polynomial mechanism. Similar idea works if your matrix is diagonal but of size n rather than size 2. look how I can benefit from my new notations. I can say if I compute the matrix A take lambda identity, if I compute such a matrix, the result will be, like in here, you see, the result will be a diagonal matrix, so I can benefit from my notations again. Look at this. It will be a diagonal matrix with entries A1 take lambda, A2 take lambda, A all the way until AN take lambda. You can't deny it's a very handy notation when you deal with diagonal matrices. It saves you lots of time and lots of space when you write things. And so when I compute the characteristic polynomial, determinant of a diagonal matrix, something we know from the first semester, just a product of diagonal entries. The result will be like this. So my polynomial again just comes readily factorized, and I can identify all of the roots right on the spot, A1, A2, AN. Those roots we guessed before. Yeah, we just guessed them before. This is a writing for identity matrix with my new notations. Diagonal matrix with n, with n identities on diagonal. What's the time? 37. Okay, so I'll show you one example where like you go all the way, it's not a non-trivial example where you need to actually solve the characteristic polynomial. That will be the third example from my first slide. Remember the example on my first slide today, there was two diagonal examples, and there was one example where we needed to test that the given vector is in fact eigenvector. I will finish that example now. I'll find the other eigenvalues, and we're supposed to have 3 of them, remember? Because now we know that the eigenvalues, they're always roots of the characteristic polynomial, and degree of that polynomial is the same as the size of the matrix. So we need to, I'll finish that example now. So this example again, I'll just show you this. Yeah, that's example. That's something which I call example of spectral analysis. That was the matrix on my first slide. So if I had this matrix just by itself, and if I do spectral analysis, I will need to start from characteristic polynomial. There is no any other options here. Okay. There may be some other options, but the rule of thumb is that just like this characteristic polynomial is your best bet unless you see other effective ways to do it. So I will take this matrix, A take lambda identity of appropriate size. Here it is. I just took my A, and from the diagonal, I subtracted lambda, you see, from each diagonal entry. I took away one of lambda. For this one, I need to find the determinant. The result will be polynomial of degree 3, and here you will need to use your skills in evaluating determinants. You remember the skill. Normally when you do that, you do this row decomposition or column decomposition. I'm just trying to remember which way I did it here. Yeah, most likely I did the row decomposition, so here's my visualization for that. I'm going to drag this cross across the first row, and for each of the position of my cross, I will find the term in my row decomposition of determinant, isn't it? So it's the first position of my cross. The result will be, here's the computation, actually, just look into that. So for this term, it corresponds to the first position of the cross, negative lambda, it's here, and the bracket, this bracket, it's a determinant of this minor, of this smaller size. It's negative lambda times 9 take lambda and plus 24 right here. Now you drag your cross to the next position, And this last term 20, it's the whole representation of the second term which corresponds to this cross position, for this position of the cross. 1 times the minor. Minor consists of this column and this column. Because of the 0 here, the only term is 20 times 2 with extra negative. That's why it's plus. And obviously, when you put your cross in the last position with 0 here, nothing comes up because of the 0. I hope you have enough experience with evaluation of determinants to realize that when you do this row or column decomposition, it will be a smart choice if you choose column or row with as many zeros as possible, because the more zeros you have, the less computations you'll have in your evaluation. That's why I chose the first row, because of that one extra 0 in that row. Anyway, that's my polynomial. If I do a full expansion, that's the canonical shape of my polynomial. As predicted by the general result, it's a polynomial of degree 3. And all of the eigenvalues must be solutions to this. At this stage, of course, you need to find the others, all of the solutions to this cubic polynomial. We don't have like a general method to do that. Here we need to think of something smart, something beautiful. Well, in this particular example, I can borrow our knowledge from first slide today. In that knowledge, remember, we were given a vector, which we tested, and the vector turned out to be eigenvector, and we even discovered the associated eigenvalue. So from the general considerations, I can be absolutely sure that that value we discovered will be a solution to this polynomial. And that's a little extra knowledge I bring into this consideration to make my search for the other eigenvalues easier. This is the extra knowledge. We can double check this knowledge. If you take this, if you test this number across the polynomial, we can be absolutely sure it will work. If it doesn't, something wrong here. It's the indication that you made something wrong in your computation of your determinant. And I think I have a pre-computation of this verification. Look, if I take 5 across this, negative 125 for the cube, 9 times 25, negative 24 times 5 plus 20. I insist all of this adds up to 0. Is that right? We can think in terms of, we can't think, this is 120. It's 245. This term and this term together, it's negative 245. This one is 250 less 25. It's 225, and the difference is 20. That's right. It adds up to 0. Now, your skills in factorizing polynomials comes handy, because if you have a cubic polynomial and you know one root of it, the rest of the roots can be discovered with some effort, but they can be discovered you have a robust method to do that. All we need to do, we need to factor out the bracket lambda take 5, isn't it, from this polynomial? Here's the factorization. So if I start off from my polynomial, yeah, that's right. You see what I do? I intentionally create this bracket because I know 5 is a root. I start creating this bracket, so I split this 9 lambda square in two pieces, like this, because if I do so, these two together, they make up a bracket lambda take 5. Now, I split this 24 into two pieces like this, again intentionally, with intention to factor lambda take 5 from these two terms. And then the remaining bits, they must add up into another bracket lambda take 5. That's my factorization, first step. So here we go. First two brackets here. Common factor lambda square, or negative lambda square, came up. The bracket lambda take 5 appeared. The other two, common factor 4 lambda, came up. Lambda take 5 bracket, again, becomes explicit. And final one, these two together, negative 4 common factor, lambda take 5, right here. Good. So lambda take 5 is a common bracket across everything. That's the remaining bits. That's the remaining terms, which is a quadratic polynomial. And for those we know how to factorize them. In fact, this is a perfect square. This is a perfect square of these two. And that's a complete factorization of my characteristic polynomial. Now from my general considerations, I know that every root of this polynomial is eigenvalue. So here we go. One of them is 5. We knew that before. But the second eigenvalue just came up. And my polynomial knowledge tells me that the second eigenvalue has multiplicity 2. So in the eigenvalue universe, I will say that the eigenvalue 2 has algebraic multiplicity 2. That's a new term which you have to remember. When the eigenvalue in a characteristic polynomial after factorization comes with a degree higher than 1, that's something which we call algebraic multiplicity. It's just a term which you need to remember. We just do the prefix algebraic because for the eigenvalues there will also be something which we call geometric multiplicity, and there will be a way to find it later. We'll discuss this with you. Okay, so this is just the beginning of the spectral analysis. We need to find now the eigenvectors associated with each of these eigenvalues. So let's just try to do that. For the value 5, one vector we know, it's from the first slide today, the one which we tested already. I wonder if there are any other vectors. Let's just see. So how do I test for that? Remember, the eigenvectors, it's those elements which are in the null space of this matrix. Every element, every non-zero element in the null space of such a matrix is the eigenvector. So here's my matrix. I use a particular value for lambda, 5 it is here. I write up this matrix, whole matrix, here it comes. I just use value 5 across here. I can be absolutely sure that this matrix will have a non-leading column because that's the nature of the eigenvalue. And I need to describe the null space for this matrix. So here's my description. I take this to the row echelon form. That's the pre-computation for the row echelon form. Okay. As predicted, I have a non-leading column. If you end up with something which doesn't have any non-leading columns, you did something wrong. You need to track it down, track it back every step and find a place where you did so wrong. But trust, I mean, like you have to take this as a sign or as a double check. This row echelon form, must have a non-leading column. It may be more than one, but at least one will always be there. And now I describe the null space. How do we do this? We just parameterize the variable which corresponds to the non-leading column. x3 I set to t. I solve for the x2 from this line. That's a solution, 1/5 of t. And I solve for x1 from this line. That's a solution for x1. If you put this into the vector form, this is a vector form, it is a complete description of my null space. Every element of this null space is eigenvector. If you just rename your parameter like this, you will make it look a little bit neater. And you can recognize the vector which we had on the slide 1. That's the vector which was given to us as a candidate, and we tested that vector. That's how we discovered our first eigenvalue, if you remember. And this analysis tells me that there's no any other vector besides scalar multiples of this vector. One extra observation which comes from this analysis is this. If you have an eigenvector, if you scale it with any other number, the result will also be eigenvector. It's right here. Because eigenvectors together, they make the whole subspace, eigensubspace. Right. And in fact, this gives me the opportunity to introduce the second idea of multiplicity, geometric multiplicity. Geometric multiplicity of an eigenvalue, this is dimension of the corresponding eigensubspace. So algebraic multiplicity, it's the multiplicity of your eigenvalue when you factorize your characteristic polynomial. But geometric multiplicity is just dimension of your eigensubspace. In this case, in case of 5, your eigensubspace, E5, is a span of one single vector, this vector. Meaning that the geometric multiplicity of this eigenvalue is 1. In fact, the same as the algebraic multiplicity, 1 here. Yeah, I just realized we can introduce this term geometric multiplicity right now together with algebraic multiplicity. That's another term which you need to remember. Geometric multiplicity is a dimension of the eigensubspace. Now, we still have another eigenvalue to study, the second one here, 2. Here's my analysis of the second eigenvalue. Again, I have to start off with the matrix like this. A take 2, I 3. Here's the matrix. It's from here. Right here. Again, I need to take this to the row echelon form. Here's the pre-computations. As expected, we have at least one non-leading column. So when I try to do, when I next describe the null space of this matrix, I will parameterize the unknown which corresponds to the non-leading column, x3 it is. I solve for x2 from this line, is a solution, and I solve for x1 from the first line in my row echelon form, is a solution. I convert this to the vector form. I rename the parameter to avoid dealing with fractions. And that's my null space. E2 is a span, again, of one vector. And I can say now that the geometric multiplicity of the second eigenvalue, unlike the first one, is different from its algebraic multiplicity, because the geometric multiplicity of 2 is 1. Dimension of my null space is 1 here. It's a span of one vector yet. Algebraic was 2. But the geometric multiplicity is 1 in this case. And that's how you end your spectral, that's a complete spectral analysis. You see, we found every eigenvalue. We found every eigensubspace. We identify the dimensions and the bases in these subspaces. We identify the multiplicities. Any questions? Okay. There will be some shortcuts. I mean, with some experience, you will develop shortcuts. I'll discuss some shortcuts in class. I mean, when you can do like a more efficient study. But in principle, that's the spectral analysis you will be doing on a few occasions in the yellow book. We're done. Thank you very much. Enjoy your break. Thank you.